All right, so today's class is about the longest path in contrast to earlier lectures about finding shortest path and shortest path. Okay? So let me remind you and remind me, since it's been a bit of time, what we've been up to roughly since the lecture before the mission is, well, we started with a stat problem, which is a hard problem. The idea of you're just given some generic Boolean algebra stuff, and you want to know if there's something that makes it come out to be true. Right? And roughly, can you answer kind of Boolean riddles in a way? And in general, this is hard. But even right, is there a polynomial time algorithm for this problem, which otherwise seems very computational and feels. But besides this problem, we looked at special cases of this problem, like CNF stat, where the formula is kind of nice and clean. It's an and of ors. We looked at 3-sat. We looked at circuits. Right? We looked at all these variations of this problem, special cases, general cases. And what we found out is that while we can't figure out an algorithm for any one of these, we just figure out that there's an algorithm for one, if and only if there's an algorithm for the rest, which is an interesting conclusion, even if it's not a constructive algorithm. Okay, and then we pushed that even further to do 2-sat and max 2-sat, where something kind of funny happened. Max 2-sat turned out to be just as hard as 3-sat, and 2-sat for some reason is super easy. We can do it in linear time because somehow we're able to turn this into some kind of reachability style problem on a DAG by modeling this implication graph. Right, but you would think there's not a big difference between 2-sat and max 2-sat, but computationally there's like a massive difference, like two completely different things. Well, there's supposed to be a slide about subset sum, which we did last time, but I forgot. Anyway, so subset sum was also a very simple looking problem. I give you a bunch of numbers and a target and say, okay, can you take some subset of the numbers and add it up to the target? And that might seem easy, and in fact, we can even come up with a reasonable algorithm if the numbers are small or something like that. But it wasn't a polynomial time algorithm. And it turns out that you can roughly take a 3-sat formula and pack it into a subset sum problem. And so we showed that subset sum, actually, as simple as it looks, may be quite hard to solve as well. The difference between subset sum and the earlier lectures is that subset sum doesn't look like stat. At least not to me. Even after the reduction, it's still a bit of a stretch sometimes, right? And so that should make you wonder, is that hiding in other problems, right? If it can hide in numbers, right? And today we'll be seeing if it can hide in graphs. So here is today's problem. So here, I guess I'm presenting a directed graph you've seen before, I think. Just copy and paste it. And the goal is to find the longest path, or just the length of the longest path in terms of number of edges in the graph. Now, by path, I really strictly mean path in the sense that vertices can't repeat, so not generally walks. Okay, so you cannot go back to a vertex you've already visited. It's really a strict sense. So the word path, sometimes that's called a simple path to stress this distinctness. A special case, and something that mathematicians have long been interested in, is a Hamiltonian path. A Hamiltonian path is a path that visits all the vertices. Right, so is it possible to visit all the vertices exactly once? No repeating and not omitting any vertex. Right, so sort of a slightly easier problem is taking a graph and asking, does it have a Hamiltonian path, in particular a path of length n minus 1. There will be n vertices and n minus 1 edges in a Hamiltonian path. This is very similar, some related problems are what's the longest walk in a graph. I think that might show up on either homework or an MCQ. And shortest path, which we discussed in detail a few weeks ago. So longest path. All right, for this graph, is there a Hamiltonian path? I saw some no's. Who can explain, or does anyone have a succinct? Yeah.
So again, pass that to n squared.
Yeah.
The vertex on the very left.
Yeah.
And
Think. Yeah.
so is the one on the bottom.
Ah. Okay. So we have two sinks. I mean, two vertices that only have incoming edges and no outgoing edges. There's no way to have a Hamiltonian. All right. How about the other problem? What is the length of the longest path in this graph? You can start anywhere. You can end anywhere. What's the longest path you can take? You guys might need to stare at this longer, so I'll give you more time. I don't know the answer to this. I'm trusting you guys to. Seven. Someone got 7? By the way, there's 14 vertices out here. This is not a big graph. All right, 7. Anyone beat 7? 9? Okay. Anyone beat 9? All right, how'd you get 9? Where should I start? Yeah. This one? Okay. I'll start here. Down left. Up left. Up. To left. Down. To right. This is pretty good. Down to the right. Up to the right. You could do a little better. Yeah. Squeeze that lemon. All right. So how many edges is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay, that was your 9, I guess. 10 vertices and 9 edges. Anyone do better? Okay, that's pretty good, I think. Okay, good. All right, so that maybe the answer is 9. We know the answer is at least 9. All right. Okay, so the problem makes sense. Okay, so we're going to look at this problem in 3 settings. We'll look at it in DAGs when there's no cycles in the graph. We'll look at it in directed graphs, like we just did. And we'll look at it in undirected graphs. That's as if we had both directions on every edge. Okay. And so, these are 3 different problems, so they may have 3 different conclusions. Okay, so we'll hope for each one, figure out if there's either a polynomial time algorithm or if it'll turn out to be just as tough as 3 stats. Or you could not vote, as always. All right, who's not voting? Okay, even the people who are eating are going to vote then. All right, okay, who thinks that, we'll start with that. Who thinks we can come up with a polynomial time algorithm? Okay, many of you. 90%. All right, and who thinks it's going to turn out to be tough? 2. Definitely some liars. I know at least 3 of you that I spotted. Okay. All right. Okay, so most of you think that for DAGs, we can do something constructive. How about for directed graphs? Who thinks we can get a polynomial time algorithm in directed graphs? All right, 8 people. That's like 20%, 15%. Now, who thinks it's going to turn out to be tough? Okay. 85% minus 1. Okay, and then, no, that doesn't matter. Okay. All right, lastly, undirected graphs. Who thinks we can come up with an algorithm for undirected graphs? Oh, less people than before. And then who thinks it'll turn out to be hard? Okay, nothing very much. Okay. Okay, here's my question. What? Oh, okay. A lot of questions. One question is, why did more people think undirected would be harder than directed? Or why did more people think undirected would be hard than they thought directed would be hard? Well, yeah. Right. So undirected is a special case of directed. Right. So if you have an algorithm for directed, then you definitely have an algorithm for undirected. I can take an undirected graph and add both edges. Not necessarily vice versa. It's not clear how to turn a directed graph into an undirected graph. Sorry? Yeah. Well, I'm just saying it's obvious how to go from a undirected graph to directed. It's not obvious how to go from directed to undirected. Maybe it's possible, maybe it's not. There's a lot of room. But at least one direction should have been obvious. My suspicion is that the 15% from directed looked around the room during the directed vote and changed their mind for the undirected. I don't think it has anything to do with logic. Okay. All right. So 15% of you have no guts. Okay. Fine. But okay, so let's take directed graph. For those who thought there's going to be hope for a polynomial time algorithm, maybe change your mind later. What was your intuition? Oh, you thought maybe it could be reduced to DAGs. Okay, so maybe you also voted for DAGs having a polynomial time algorithm, and we've seen, okay, if you could do a DAG, then you can do a general graph for, reachability problems for. I think that's reasonable. Okay. And then, why did many of you think it was hard? It's just like max 2-sat. I don't know how many people agree with the sentence that Hamiltonian path looks just like 2-sat. But I guess 2-sat, you could draw a graph, and then there was some graph stuff. Although the graph wasn't necessarily useful for max 2-sat, right? That graph we drew for in the 2-sat lecture, the implication graph, was particularly useful for 2-sat because I know that if I set this to be true, the next one had to be true or something, because I had to satisfy all clauses. That graph wasn't actually that relevant for max 2-sat because there wasn't the forced implication. Okay, maybe that's anyone else have any ideas besides auspicious connections to max 2-sat? Bad vibes, maybe. Yeah, as far as at least trying to distinguish between DAGs and directed, because cycles make a big difference. Certainly you guys got the direction correct. Directed should be harder than DAG, and that's reflected in the vote. Okay. Or it can't be easier, All right, so, okay, let's move on. All right, so we're going to start with DAGs then. We're going to go in the listed order. All right. All right, the longest path problem in a DAG. Okay. How do we go about solving this? Well, okay, what's the one thing we know about DAGs? What are they characterized by? Sorry? Oh, there's a sequence, yes, yes. Or what does DAG stand for? This is a midterm question. It's an acyclic graph, right? There's no cycles. Everyone got that right? But historically, no. Right, so no cycles. So in particular, every walk is a path. Okay, so we could have also written this question as longest walk in a DAG, and it would be the same because all walks are paths when there's no cycles, right? But this is nice because at some level, like path, you're a little bit worried about repeating vertices and like the history of who you've already visited as you try to navigate through or something, right? But there's no chance of revisiting a vertex in a DAG. You don't actually have to worry about who you've already visited. You can just worry about, just trying to have a long walk. That's already very helpful. Okay. Now, so now let's say I want to figure out the longest walk or the length of the longest walk in this DAG. How might we go about making an algorithm? Sorry? Source? Source what? Oh, peeling sources. Okay, so let's say I start here and I remove it. What do I do? So I just remove this. Okay, add point one like that. Yeah, so I just mark one like that. Okay, now I peel this one. Okay, so now I want to do max of 1, comma 1. Okay. Okay. So this will be 1. Okay, so you want to do the max then as I peel things. All right, so now this becomes a sort. Suppose I peel this. What am I supposed to do? Okay, so I'm always taking this number, adding 1, and taking the max. Okay. Something like this. It's the max of 1 or 2, so this becomes 2, is what you're thinking. Okay. And then I guess this will become 2, like that. Now I deleted this. All right, next I delete this. So I think by your logic, this will become 2, and that remains, the other one remains 2. I do this becomes 3. This seems to kind of work. I guess I can remove this as a source. This becomes 4. This becomes 4. I can remove this. This becomes 3. Remove this, that becomes 4 again. I remove this, that becomes 5, and I get 5. Okay. How would I prove it works or formulate an argument? Okay, induction. And what would then be the sentence? Like, how would I frame it? What would I actually write down? Yeah, so we need an induction hypothesis, and there needs to be something that's getting smaller or something, right? How do we actually prove this? A full, complete proof. I see the logic, right? I think we agree on the algorithm. I think you just restated the algorithm, right? But now how do I argue that, oh, this really, really works no matter what? As opposed, hey, that seems to go pretty fine in this 8 vertex example, so let's just throw it in the computer. I say this partly because maybe someday you're working on a more complicated problem on a DAG, right? Where it's not as maybe obvious as this might appear to you. Yeah. Okay, so assume, okay, proof by contradiction. So I think the statement that you want to look for the contradiction in is roughly this algorithm is correct, or this algorithm returns, okay? Now one thing, sure, but suppose we did, okay, so claim is that the algo returns length of longest. I mean, that's what we want to prove. Suppose you want to prove this by contradiction, right? Okay. So now I tell you, okay, suppose it didn't. What's the next sentence? Yeah, okay, so it does, so let's say that returns something that's not the length of the longest path. And now how do we proceed? So you ran this algorithm and it returned the number 6 instead of 5. Now we have to kind of dissect that, right? This is where it's getting tough to articulate. Oh, well, maybe something analogous would, yeah, suppose it did return a long path, it returned a path of length 4 or something. Okay, so let's say that the algorithm returned, I mean, if you want to do returning the path instead of the length, suppose for some, assume by contradiction it returned this path, which is 4 instead of 5. It's just like Dijkstra, but not min-max. So see, this is like very, I don't even know what that really means, right? Okay, so, well, first of all, well, maybe at a high level, saying just like X except Y is not really much of a proof, right? I mean, it's more of a comment at best. Yeah. So I think what you want to say is like, okay, so if I look at this, for example, the mistake occurs here, right? And I would love to say, okay, at that stage, the algorithm messed up, right? Well, here's what's kind of, I think, going on and making the argument a little bit tough, right? Is that you kind of want to pinpoint like a state, right? And say, oh, this is where it kind of, but this is like somewhere in the middle of the algorithm, right? Deep in the algorithm or something. And the statement we're trying to prove, even if I wrote returns the longest path instead of the returns the length of the longest path, doesn't seem to allow us to go into the middle of the algorithm, right? Because it's just talking about what's happening at the extremes. So in other words, this sentence is a little bit harder to kind of go into the algorithm and do one step at a time, right? It doesn't, especially with like all these numbers, 1, 2, 3 floating around, right? Those aren't even captured in a sentence, right? Because the input starts with a graph, and then now in the middle of the algorithm, you're annotating it with these numbers. So whatever you're trying to, if you're trying to prove something that's going on in the middle of the algorithm, your sentence might need to actually take into account the numbers or something, right? Because that's part of the state in the middle of the algorithm, so you can pinpoint the flaw or the contradiction or something like that. Okay, so I think, so I want to explore what's on the surface, a slightly different way to frame going about this. I think you can reverse engineer that they're going to ultimately do something very similar. But it'll maybe be easier to see why it's correct, easier to argue why it's correct, and ultimately hopefully give a recipe that's also more transferable to maybe more complex problems on that. Okay? So as opposed to this kind of sort of sequential marking algorithm, which I do think is a correct algorithm, I would like to, any other ideas, I guess? So something besides, yeah. Oh, okay. Okay, so let's make all the edges negative. I can also add like a super source S that's connected to every vertex, and a super sink T that's sort of connected from every vertex. You say, okay, go from S to T with S Q total minimum length, right? So starting at that super source S will choose the right starting point, and that's going to that super sink T. I didn't draw all the edges to T. Will choose the right ending vertex for you to do correctly, and you add -1 everywhere. Okay, that won't work, but why? Sorry? It's true. There's no negative cycles, so that's good. Yeah, you could find the shortest path. I'm telling you, Dijkstra's algorithm will not find the shortest path in this graph. What's missing? Why will Dijkstra struggle here? It's actually not because of the presence of negative cycles, or lack thereof. Yeah, so Dijkstra can't handle negative edges at all. So in general, if Dijkstra is, I don't know, trying to go from S to T, even if these are all negative, right? -1, -1, -1. So distance to T should be -2. Dijkstra might conclude that T has distance -1 before exploring the other path, right? When Dijkstra chooses something, it makes up its mind forever. Okay, so Dijkstra actually doesn't work with negative edges, even if there are no negative cycles. Sorry? Bellman-Ford would work, but now you are going to look at like an M times N running time. A little slow. Okay, I want to do faster. Okay, so we're rolling out kind of marking-based algorithms, or just sort of like rolling out Dijkstra, rolling out Bellman-Ford. Any other buzzwords? What's the most annoying thing I have us do in this class? Right proofs, okay. And then what do I force you to do at the beginning of each proof, or to frame a proof? Recursive spec. Okay, let's do a recursive algorithm. Okay, that's your worst nightmare. All right. So let's do a recursive algorithm, starting with a recursive spec. Okay, so something that should capture the problem, but hopefully has enough parameters and variables that we can also define subproblems. Okay. So who wants to propose? I'll propose the acronym LW will stand for longest walk. Okay. So you need to fill in the parameters and then give me a sentence description. All right. Sure. The graph. Let's just say the graph is fixed. Okay. Some vertex V. Okay. So LW of V, which you call a source, and what should a sentence be? All right, length of longest path or walk, doesn't matter, starting from V. Length of the longest walk starting from V. Okay, good. And so what's kind of nice about this, right? So I'm here at V, right? And if I wanted to, use recursion, how might I, let's go here, I have it. Length of the longest walk from V. Okay, this is nice and clean. So I'm at V right now, right? And recursively, I can try to figure out other things, right? So how might I take how would I solve for V? Recursively, I would probably replace V with other vertices. But what are those vertices and why, etc.? Yeah, okay. If I'm looking for a path starting from this V, the first edge needs to go somewhere, right? So we can, try out this vertex U and compare it to this other vertex, whatever it is, W, or something like that, right? Okay, so, and recursively, I'll assume that I figure out the answer to those, right? Why is recursion okay here? We're in a graph, right? Could be dangerous. There's no cycles in particular. So you'll never have a cyclic dependency because that would be tracing a cycle in the graph. So DAGs are actually made, just ready-made for recursion. So, all right, so how might I, okay, so let's implement this. You just tell me what to write. So longest walk from a vertex V. Do base cases first, etc. But all right, so I'll write for all vertices U that are out neighbors n plus of V. So sometimes n plus of V is like out neighbors on V, meaning I can go out one step. L W U. Okay, fine. The only awkward thing is what happens if there's no out neighbors. Okay, so 0 if V is a sink, meaning there's no outgoing edges. And then 1 plus the best one otherwise. Okay. All right, nice, simple algorithm. All right. Now, how would you actually set up a proof of correctness? Okay, so you would prove by induction that for every vertex V, LWV returns a length, right? But induction needs to be something like, oh, there's a base case, and then you can add on to it and stuff like that, right? So, before there was always like a clear n, n minus 1, n minus 2, stuff like that. Yeah. Yes, anything. And so in general, where does the ordering come from? We need some kind of ordering, right? Like you can always take any induction argument and kind of order it from the simplest to the big, yeah. The topological order. So, there's some kind of way to list vertices so that the edges are only going to the right, right? And these are also the recursive calls. Recursive calls are only going to the right. So the base cases are down here at the end. And then, so in other words, you can do induction on the topological order. So if once I've done the last 10 vertices, or from your point of view, the last 10 vertices, then I know I've done all the sub-problems so that I can do the 11th, right? Because it's only going to depend on something down here, okay? So the topological ordering really formalizes the connection between induction and DAGs, right? It gives you some ordering where recursion is safe, and you can actually build it from bottom up. Okay, good. How long would this algorithm take? It could be kind of slow because you're going to explore every path. Like V is going to go here, and then U is going to try this one, and U is going to try that one. This algorithm is actually exploring all possible paths from every vertex. It's actually not very fast. All right. Excellent. How do I make it faster? Okay, we can save the answers. There's no reason to save solve any problem twice. All right. So if I use dynamic programming, I save the answer for each subproblem. What's the running time? Right. Yeah. M plus n, you said? Okay, so why? Okay, so here I'm summing over all the vertices, the time to solve that subproblem. And so for a particular vertex, what's the running time? Sorry? Yeah, or maybe 1 plus out degree, just in case it's a single. Okay, so it'll be 1 plus the out degree of the vertex. And now if I go through all the vertices and I'm just summing up how many edges leave it, how many edges leave it, how many edges leave it, I end up counting every edge once. So all those degree pluses, which stands for out degree, that'll sum up to the total number of edges. And the ones will sum up to the total number of vertices. Okay. So you can do this quite fast. I think implicitly this may not be so dissimilar from the marking idea from before. Or at least it has similar ideas underlying it. But this is so clearly correct and easy to argue it's correct. And look how short the algorithm is. I don't have to, it's just like one line, right? So that's what's great about it. Any questions? All right, so this is something much more general, which you guys will learn from the homework. So DAGs. You can often do dynamic programming or caching tricks on DAGs because you have the topological ordering, right, which makes it very recursion friendly, and then you save your answers and boom. It's often super fast. It's often m plus n time even. Okay, so this is very interesting. Is that going from a general graph to a DAG can make a big difference. Graphs are often much easier. Graph problems may be much easier in a DAG than they are in a general graph. Okay, so I'll give you more complicated problems than finding a longest path. But this general high level of idea of, oh, can I set up something recursive and then do something kind of locally complicated? But otherwise, kind of globally simple because you're just doing one step at a time. As soon as you define the subproblems, you're good. Right? You're basically done. Okay. All right. Okay. So that's DAGs. The DAGs, we can actually solve this problem super fast in linear time. All right, so before, I think 85% of you thought it was going to be hard. 15% thought it was going to be easy, although many of you changed your mind. Apparently, that's probably wrong. So, my question is, I want to see if anyone's going to change their mind. Okay, so we just did DAGs. DAGs turned out to be really easy. As I move on to directed graphs, I want to take a second poll. Who thinks that we can come up with an algorithm for this as well? Got like 6 people. And then who thinks that despite our success in DAGs, those turn out to be tough? And just not everyone else. Okay. Okay. All right. So it is going to turn out to be hard. So whatever. I guess maybe just from the perspective of what are the odds I'm going to get through a whole lecture without any hard problems? Probably. No. All right. So. Okay. So we're looking at the longest path problem in a directed graph. And to show it's hard, we can even look at a special case. If I can show a special case is hard, that shows a more general problem is hard, right? So we're going to look at whether or not G has a Hamiltonian path, whether there's a way to traverse the graph if it's at every vertex. And that, even deciding if a graph has a Hamiltonian path or not, is going to be hard. Okay. All right, so how do we go about it? Well, first, does anyone want to throw out any fun ideas? Because, of course, once I reveal at least one approach, you'll never get to guess again. Yeah. Okay, so I think this is a good idea worth exploring, even though we will go the opposite direction. So this idea, which has worked for other problems, right? I'm given a general graph that has cycles. Can't I do something like collapse the strongly connected components, right? And then maybe figure out a long path in the DAG of connected components with lots of edges, and maybe uncontract it, right? And then within each component, I just have to figure out how to go from in to out, which I know is possible because they're connected within a connector. So there's some, okay, so once I know I'm waving my hands a lot. Once I uncontract the graph, right? So like my longest path in the DAG are now just sort of like these sporadic edges. And I have to kind of connect them within the connected components, right? In other words, always is a connection because they're strongly connected components. So there's some way to fix and get a path, right? So that algorithm does output a path. And there's a way that it's efficient, right? It's in polynomial time and stuff like that. So actually it checks a lot of boxes. So what goes amiss? Yeah. Why? Okay, so that part where we find a path within the strongly connected component, right, to fix the path from the contracted graph, the contracted path, is not necessarily the longest within the connected component to go from in to out, right? So, and maybe another way to put it is, what if the whole graph is strongly connected, right? So then the algorithm just contracts the whole thing to one vertex, and then of course there's nothing to do. You say, oh, it's zero, and you uncontract it, and now you're left with the original problem. Right? So, so it turns out that even within a strongly connected component, so even if I told you the graph is strongly connected, it's not clear what to do. So that's maybe one thing to look to is like, oh, would this problem be easy or hard in a strongly connected graph? That's the part where we weren't able to quite fill in. The rest actually made total sense. Not a bad idea. Okay, so having exhausted that approach, well, unless anyone else has an algorithmic idea that I'm happy to discuss, otherwise we'll try to show it's hard. Now, I'm just wondering if anyone has any wild ideas. I'm not really sure what one could come up with to try to demonstrate that this problem is as hard as that. Yeah. So we should also remember the direction, because right now you're turning a graph into a SAT problem, which would demonstrate that SAT can solve Hamiltonian paths. But if we were already convinced that SAT is pretty powerful, then that's not as dramatic as the opposite, trying to show the Hamiltonian path, the silly problem with graphs, which is just fun, right? Graph problems are fun. That's for kids, right? For me. How can that solve something as broad and general as SAT? Okay, so at least to get this set up, at least let's make sure our directions are correct. So we're going to, I guess it doesn't have to be 3SAT, but we can assume it's 3SAT. But we want to take a SAT formula and somehow produce a graph, a directed graph, so that whether or not this graph has a Hamiltonian path tells us something about whether or not the formula was satisfiable. Okay, but the input is a formula. Get that clear? And I want to make a graph. All right. Okay, so I think one. Okay, so let's say you have some formula. For some reason, I used phi instead of f. It's like the same, I guess, in Greek. All right. So when I'm looking at something like f or phi of x1 through xn, right? And you're going to assign each xi to either 0 or 1. And at some level, how can I model, like, so in graphs, I'm choosing paths, I'm choosing edges and stuff, right? I'm choosing ways to get through a graph. And here I'm going to choose an xi to be 0 or 1, right? A binary decision. How might I try to model graphically a binary decision? This is also hard to guess, but you have a slightly better chance than last time. It's more focused. Sorry? All right, so which outgoing edge? So maybe you're saying, so I have some vertex v, maybe I have some vertex vi that corresponds to variable xi, and somehow I create two edges that are leading it, and somehow this should represent selecting 0, and this should represent selecting 1. Okay. That's an idea. Any other ideas? Yeah. Okay, so let's say I have a clause x1 or x2 or something. So I'll make a vertex corresponding to the clause, and then I guess edges corresponding to the variables. Yeah, okay, so I need okay, so that's a reasonable mapping. Okay, so what am I trying to satisfy in each problem, right? On one hand, I want to visit all the vertices. On the other hand, I want to satisfy all the clauses. So that suggests there should be a clause for each vertex, right? We're visiting the clause should somehow correspond to satisfying it in some setup. That's good. Okay. Yeah. Now, in the same sense that, remember, subset sum, we sort of had to add the constraint that each xi had to be 0 or 1, and then we had a digit for a small digit for the variable, because you can only choose to be 0 or 1 and not both. In the same sense, you can have as a constraint that xi has to be assigned 0 or assigned 1. Right? That could also be a logical requirement, so to speak. Okay, so all right, so here's same slide, I don't know why. Okay. All right, anyway, here is, for at least this question, how to model it as a graph, a different approach to having two outgoing edges. I can set up for a particular xi a long path with a bunch of vertices in the middle or something, right? So I can do this for each vertex and worry about how to connect them later. So in other words, for this particular variable xi, I've created some path with edges going in both directions. And the only way to get in and out is at the end of this path. Right? Now, if I want to visit all the vertices in the middle in a Hamiltonian path, there's only two ways to go about it. Right? Because I can't go there and back. Right? Because then I'll be revisiting the same vertex. So if I want to visit all the vertices, then I can go from left to right, or I can go from right to left. So that's another way to sort of say, okay, you have to choose one or the other, right? To satisfy the requirement of the Hamiltonian path, you're going to have to go along this path in one direction or another. Okay? And okay, so from left to right or from right to left, and I can assign, meaning to each one. Henceforth, I'm going to interpret left to right as assigning xi to be false, and from right to left as xi to be 1. So that's what we'll do for the gadget. All right. By the way, this reduction is going to be like very creative. I don't know if you can guess it. Okay, so, and we can hook these up like in a big ladder, one for every variable xi. Right? So imagine there's n layers. Now, Hamiltonian path. So I'll note two things. We have those bidirected layers, paths on top, and then I've kind of connected them with edges going down, right? So if you look, these light blue edges are going down by path, and they're also crossing. Okay? So if this were, there's nothing to do with clauses yet. We'll address that next. But in this kind of setup, what does the Hamiltonian path have to look like? Yeah. Yeah, it has to kind of start at the top and cross over and then, right? So it must start at one of these corners, like, let's say I start here and I go across like this. So maybe that means, oh, I'm setting x1 to be 1, right? And then I have to, do one direction or the other. So I have two arrows at my disposal. So I could go down and go across to the side. I can go down and then across to the right, like that, maybe set x2 to be 0, or I could have taken the diagonal, like I can take this diagonal. Fortunately, green looks a lot like blue, right? I can take that diagonal, and then I can go across this way, right? So I have this diagonal so that for each path, I can choose which direction I want to go, okay? So in some sense, every Hamiltonian path in this kind of ladder-like configuration has to declare like a direction for every xi, which I can interpret as a decision, setting xi to be 0 or xi to be 1. Yeah. Those are just vertices. Well, they force us to go to visit them in the middle. I have to have at least one. Otherwise, I could just skip the layer entirely. So having at least one dot in the middle, one vertex, means I do, in order to visit, remember Hamiltonian path, I have to visit every vertex. So I have to go across the middle one way or another. The reason I have more will come up in a moment because that's going to help us deal with clauses. It'll be convenient to have extra ones. But you have to have at least one there to force you to go one way or another. Or maybe you don't because you still have to reach the corner. Okay, maybe you don't need any. So it'll be more useful in the moment. Okay. Okay, good. All right. Okay. All right, the next question is, let's take a simple clause like x1 or not x2. Okay, so, and given this sort of ladder style construction we have going, how can I model a clause? So we already have this idea. We should probably at least introduce a vertex for the clause. Okay, so you're going to introduce at least one vertex for a clause. Good. So how am I going to kind of connect it into this overall structure? Okay, so just tell me, I try to make it a little bit bigger. So, okay, we'll probably do something with the x1 and x2 paths up at the top in particular. So, what should I draw? Okay, so I want to probably introduce some vertex, right? Maybe I'll draw it in between the two layers. Okay, so this will be the vertex for that clause, right? I've drawn one dark red vertex. Okay. But how might I add some edges? Right, so now I have to visit this vertex that I know. That was a suggestion from earlier, and I think that's a good idea. So let's say that going from left to right means I set it to false, and going from right to left means I set it to true. 6-1 orientation. Okay. So yeah, how am I going to kind of get that to fit into the logic we have going? This kind of graphical logic we have going. Okay, so if I'm saying x1 to be true, right, so that means let's say I'm going from right to left. Okay. The left, okay, so connect it like that. Sure, okay, so I can add this edge from the top left corner so that if I was going x1 equal to 1, I'm in there and I can just drop in. But now I still have to add some more edges, right? Like, you can't just stop there. So okay, so this node here, like that. So that if I was going the opposite direction for x2 equal to false, then I can, after choosing false, I can drop in. Okay, maybe I should make these different colors. Let's do purple. Sorry. Okay, so you suggested I add these two edges, right? Okay, but the Hamiltonian path needs to lead somehow. Can't just end there, right? But this idea is good, right? It should, the high level idea of if I'm going in the x1 equals 2 direction, it should be easy to visit the vertex. And if I'm going in the false direction, I shouldn't be able to visit, or it should be hard to visit the vertex. I think that's a good idea. Same with the true, right? So somehow we should connect the red dot to the x1 path in a way where it's easy to kind of detour and visit if you're going the right direction, and it should be difficult if you're not. So this is one way to try to do it, to just use those extreme points. It's actually going to be a little bit tough though, so I'll erase it. But it's a good first idea. Any other idea, right, to try to make it. So if I'm going in x1 equal to 1 direction, it should be easy to visit the cause. Yeah. Oh, okay. So you're saying in this particular one, I could have erased. Okay, so if I went x1 false, that means I would end up in the top right corner, right? And so I want to force x2 to be false, so I can erase this edge and force it. Oh, okay. Yes. Okay, but okay. So but when you say the point, do you mean this big red dot? Okay, but we have to figure out how to add edges to the red dot. Right now, the red dot's just floating. Yeah. We have to draw edges. You have to give me some edges to draw. Yes, of course. You'll need to. Otherwise, you'll get stuck there when you go there. So from red to the right corner, like that. You want to add that. Okay, do I start at the red, and then I go where? Like that? Is that where you want me to go, or you want me to go further? Oh, the last one? Okay. All right, I'll add that edge. Sorry. I add that edge. You want me to go further? Wait. Oh, the other side. I'm sorry. Oh, I get it. Sorry. Being selfish. Not seeing it from this. Okay, so I add that. Okay, so right now I just have a red vertex that points to x1. So I guess the opposite would be like this. Okay, so now red is a source vertex. Okay. Okay, I'll say a couple things. One is, what happens when I have a second clause? If I do the same thing, right, with some other clause, which also may have more than two variables. I'll have two source vertices out there, so of course there's no Hamiltonian path. That's one issue. The other issue is that, at least as constructed here, since the only way to get to x1 starting from red is to actually just go up, right? Because you can't go back up in this graph. Yeah. Uh-huh. Okay, so one, okay, I'll take these two consecutive ones. The one on the right, which I'm circling, edge to red, edge back out. Okay, now if I'm going from right to left, I can easily just dip down and get back on the path and detour. Right? And then I guess the same thing down below would be something like this. So if I'm going x2 equals false direction, I can just quickly detour, visit that vertex, and get back onto the path where I left off. Okay, so that's another idea, and that's nice and simple. It still keeps you within the logic, and I can do that for all the clauses. Okay, so right. Okay, okay, right. So okay. All right. So this was then the suggestion, right? I guess. Oh, I'm sorry. The directions are. That's quite annoying, isn't it? I have somehow flipped all the signs here. So this is x1 to bar, and this should be x1 is equal to 1, and x2 is equal to 0. Somehow it's like you get everything wrong or everything right. Okay, anyway. Okay, but that's the idea, right? So now if you're going in the correct direction, it's very easy to just quickly detour and visit that vertex. Get back onto the path. Yeah. Well, you don't have to detour. So, yeah, the first time you come through, you detour. And then if you also happen to choose x2 correctly, the next time you just pass by. Okay. Oh, we're running short. Okay. So you put these all together, right? So, I don't know, maybe you have a clause with 3 variables, so you have more of these edges, and you just have to, put the whole thing together. And then ultimately, you can satisfy only the clause only if you find some kind of snaking pattern that allows you to detour and visit each of the clauses along the way. Okay? And then to ultimately do this slowly, you do the if and only if. So you start with a satisfying assignment, x1 is true, x2 is equal to false. That tells you which direction to go on each one, and then you just plug in the detours based on what satisfies each clause. That gets you 1. On the other hand, if you have a Hamiltonian path in a ladder-like graph, you know that it has to go in this pattern to satisfy everything at a high level, and then the detours also guarantee the satisfying. It would take a paragraph. It would be a little awkward to write, but you just do both. Okay. All right, so that's the high-level construction. Any questions? We'll save a little bit of time for undirected. I don't know how you would come up with this from scratch, but at least it's already been done. So, okay. All right. That's a pretty creative one. Yeah, anyway, so somehow, I don't know which is more surprising, that subset sum turned out to be hard or Hamiltonian path turned out to be hard. Like the fact that sums can capture Boolean formulas, or that actually graphs can also capture Boolean formulas. There the trick was this lesson, right? Okay. All right. One of these turned out to be easy. DAG, the most general version of directed graphs turned out to be hard. That means we don't actually know the answer for undirected graphs. Undirected graphs is not necessarily as hard as directed graphs. Well, so we've already done one polynomial time algorithm. We've done one hard thing. So I could go either way as an instructor. Okay. So I'm going to take my last vote. This is for undirected graphs. Are we going to get a polynomial time algorithm or not? Who thinks we can get a polynomial time algorithm for undirected graphs? Well, still no. Oh, one. And then does everyone else think it's going to be hard? Hey, let everyone else know on their laptop. Okay. And one person on their laptop. All right. Okay. So, okay. We are going to show that the longest path problem is also hard in undirected graphs. Okay. All right, I want to show that this problem is hard. What's a natural candidate? I want to choose another hard problem and turn it into, the directed, okay, let's somehow take a directed Hamiltonian path algorithm and construct an undirected graph so that somehow figuring out if that undirected graph has a Hamiltonian path. How would you directed graph play? You have to be more creative than just removing the arrows, which is what I did in that particular picture. That's not going to work. Okay, so there's a little misleading because in general, the graph we produce will be more different looking than in my lazy. Okay. So any ideas? How do I transform a directed graph to an undirected graph? Right, the main issue is I can't remember directions in an undirected graph. Okay, so maybe we can look at it on a vertex by vertex basis, right? So here's like a vertex C that has 3 incoming edges, 3 outgoing edges. So what should I do? And so you said duplicate it, right? So, okay, I'll make 2 dots. This is from V1, and this is from V2 or something, right? So I made 2 copies of V. All right, next, what did you suggest? Sorry? Well, okay, so originally A, B, C refer to vertices in the graph, in the directed graph. So maybe A will also have 2 copies, and B will also have 2 copies. So it'll be A1 and A2 and B1, B2. Okay, so you want me to do same number then? I think you're saying A1, B1, C1, and I'll draw undirected edges. Is that the suggestion? Okay, I can write minus and plus. So what if I did in and out? Okay. So like that. All right, and then like this. Okay, so I've taken the 6 directed edges, and first I'm separating every vertex into 2 vertices, one called V in and one called V out, and I'm sort of like taking an edge that's going out of X and going into Y and turning into an undirected edge from X out to Y in. Okay. All right. Okay, now I'll link them. Okay, so the idea is, in principle, something that goes like this will map to that. Okay. You are missing one ingredient. So what's the issue with this? So a Hamiltonian path actually doesn't have to take the middle edge. So it could be doing something like going like this and going like that, right? And that doesn't really map to something in the original graph because that would actually be kind of visiting the vertex. Yeah. Ah. Okay. V middle. Okay. Now any path past Hamiltonian path, in order to visit the middle, it needs to go all the way across one direction or the other, right? So it needs to go like that kind of thing, right? And at some level, you don't actually know if it's going in the right direction, but if it's going the wrong direction, you can just look at the reverse path. So that's it. Okay, so you just add this middle vertex and you split them up, okay? And then you do the Hamiltonian argument that I won't do. Okay? So that is the construction. You'll get a more different looking graph, of course, than drawn up there, but that's right. So you split the vertices and you add one in the middle, and then you have to go from in to out on each one, and that'll map back. Okay. All right, so that shows that undirected Hamiltonian path can solve directed Hamiltonian path modulo the long sentences that I'm omitting. All right. Okay, and that's all I have for today. See you guys.